Hello, everybody. Ooh, Yep, we're studying. That's the stream today. This is like half an excuse, but like mostly the truth. ADHD. I'm kind of like minor preface for this. I have like severe ADHD and take meds, and I don't know how to. I said want to like post doing it a lot better. But for me to start a task that I know I have to do is like dragging myself up a mountain of glass shards. Like, my test is tomorrow. I've been meaning to study for the last 3.5 hours. I just don't want to do this wholly. Okay. I have my exam 1 tomorrow at 5 p.m. Right? Oh, is it 4? No, it's gotta be 5. I wouldn't do myself like that. Testing is not loading. That's cool. No, I'm glad. Yeah, 5. Anyway, we're learning stress and strain today, chat. It doesn't say my name anywhere, does it? No. It shouldn't. If it does end up saying my name, I'm just like immediately ending stream doc. I don't care that much. This is very much a not worth losing my anonymity. That's a lie. I've lost so much of it already. I think I've already said my name. There's really nothing. Oh, free body deck. That's so easy. 2, 4, yada yada yada. And that's lecture 1 done. Stress. I'm still like basic stuff that I kind of understand. So this is just you gotta force P divided by the area, and that's just like the stress, which makes sense. It's just how it's distributed. And then you have shear, which is D, which is also uh area. Issues the force is oh my god, I'm just gonna fail. Perpendicular. And then double shear. It would be more on the board. You just split the area in half, or double the area, because there's 2. Split the force in half, because you're dividing it by 2. Then bearing. Wow. That's it. Guys, we're doing so well. We only have 15 more of these. Actually, that's not so bad. I think I deserve a 5-minute break for that one. Okay, jokes aside, jokes aside. I cannot take another break. There's a specific point I want to mention. Cross section. Cross section. Compress. I have to get my mic. Oh, I forget. There's a way of doing it where you just remove the pin. Yeah. Yeah. No more stress and pin. Pinned in tension pin area. I don't even know what T in lowercase a is. Oh, I think this time's yeah. Okay, never mind. Because it's theoretically a double shear. Makes sense. Let's go another lecture. I can remove these whatever. That's why I don't care about deleting them. Stress review from last lecture. Ooh, angle. Angle easy. I fucked up my notes already. I would like to make that clear. You're not gonna get a picture of these, but I have the normal and then to the left of it because I drew it next to the red line. But I'd like to use the full page. I've drawn angle to the left of the normal. But I just because I'm really stupid. I doubt we need to know this, but good to know. Angle from what? Angle from which plane? Angle from perpendicular plane. This we don't need to know. It'll come into play later. And I mean, if I get on the test, I'm just gonna say fuck you and then kill myself. That's no exaggeration, by the way. Oh, we have the easiest lecture. Let's go. Factor of safety. literally just, if you have a factor of safety, multiply the actual stress. Or if you have a factor of safety, if you have the factor of safety and the maximum stress you're allowed to have, multiply it. Wait. I'm not wording this correctly. This is gonna be the stupidest VOD. I would like to excuse myself, being that it is 2:40 a.m. Oh, I'm such an idiot. I'm such an idiot. I have a research lab that I was supposed to be at on Tuesday. We got the paper on Tuesday morning, and I just didn't read it for Tuesday afternoon. I just didn't show up, and I have it tomorrow before my test for 2 hours. So yeah, from 9 to 11 tomorrow, I'm gonna be like, I'm so sorry. I only thought it was Thursday. I didn't even realize. It also means on Tuesday, from when I wake up. I don't mean when I wake up because I get up and immediately leave. Well, no, that's a lie. I have an hour to rot in bed for 20 minutes, then shower, and then run to class. But from that, I don't eat from when I wake up till at least 4, including a run. A full mile run or whatever, which is meant to be a 20-minute travel from one building to another building across campus, which I then have to make back because it goes research course, other course, and then back to research course, which is so cool. Deformations, yes. Give me strain. I would like to add, strain is how much material can move per bit of material, which is a really interesting metric, by the way, because it's unitless. So yeah, so if you have, let's say, 10 inches of material, and it deformed 1 inch, your strain is 1/10. Because every inch of material can strain itself for 1/10 of the total. I'm not calculating that. Well, that'll be a leaving tab open. Now these are the important big ones. And all these equations are basically the same. This is the rewrite of the other equation from last slide. We just multiply both sides by L. This is if you divide both sides by E, or the modulus of elasticity. Which is the physical change caused by stress up until proportional limit of material. This is one of the big formulas. Equals PL over A. Big formula here. Because you can literally reverse engineer this formula for any one of these values. You know the length, but you don't know area? Use this. You don't know E? Use this. You don't know P? Use this. 5 variables in one means you can rewrite it to solve for 5 different things. So for this, you have 40 centimeters, so 40 goes in length. We have a diameter. I believe it's ABC. That's what I'm assuming. So diameter, so you plugged it in with the area for whatever like diameter is for a circle, which is what? Like diameter squared over 4 pi over 4 times pi over all of it times pi times diameter squared over 4. I think. Like 90% sure. So you plug that in, you plug that in. You're the SSD, so you plug 72 in. And then you get the displacement of this in the direction of the force. Ooh. This is being stretched by 60 force, I believe. So you calculate the 60 force? No. Yes. 60 force times 30 length over like 9 over 4 pi times 100. And that's how much it would deflate here. And this one can't deflate in this direction. Well, this point can't move. So this just gets smaller. So you have the deformation here, which would be my negative to the positive of this one. And this one, I think you'd only calculate the 60 acting on it. It's like this one wouldn't move, like, necessarily past what the glass moves. Yeah. I'll leave that up because that one's like a really important one. But I can't, like, understand myself. I know no one's listening. I know it's gonna make it to this point in this video. I think ever. It'd be more funny if you do. I won't even lie. Mechanics of material person in the future of viewing this. That would be funny. That would be really funny because there's way better videos and way better teachers. I don't know where I was going with that. Ooh, yeah, I do. Do not use me for advice. I don't know, it's kind of funny that I'm doing this. Like, I will not lie. I can't believe I made it today 81. I don't think I calculated this correct. But this series will end moderately soon. I know I said a year. I got to 81 days. I might do it for a few more days. but I plan to. I can't. Bro, I'm so mad. I'm so mad. I can't even go home for spring break because the week I get back, exam Monday, exam and quiz Wednesday, exam Friday. Me when I'm scheming to be evil. All my professors getting to the scheme how to make my life genuinely miserable. I would like to add that, like, immediately after that, I think. Oh, do I still have it open? Oh, I closed it out. I should pause my music. Bum, 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 bum. Oh my god. I'm actually so stupid. You know I'm exhausted. I have a class called Mechanics and Materials and half class called Materials. Like, okay, exam 2 for Mechanics and Materials, which is this course. Let's check. Oh my god, it was this month the 2nd. No, it's next month the 2nd. Wait. Well, that's at least on a Thursday. Okay, okay, I have a little bit of time. Anything? Quiz 5, yeah. Exam 3 is the Monday I get back. Wait a minute. That's Mechanics and Materials. Yeah, the Monday I get back. Me when I collect everyone who has ever hated me, it's just my teachers. This is genuinely an evil schedule, by the way. Like, I know it's not intended to be evil, but like, imagine having an exam. Oh, I can finally take a day off. Nope, no, you can't. Wait for tomorrow's exam. Oh, okay, at least I did that. What's next? Tomorrow's exam. What's next? Tomorrow's exam. And then little tomatoes and blowtorch my home. Okay. Geometry, search string code, generalization, please load. Nice structure, made of the same material. Yeah. Elastic. Therefore, we cover elastic. Therefore, perma yield. Yield right after E meaningless. Small change in force, so it's no change in information. Small force, big, therefore, strain, hardening. Limit, increase after yielding. And every time you go, it kind of like resets the point. So like this is the elastic modulus. If you like get to here, it kind of drops down there. So it is harder again, and you do have to like reach that stress for it to start breaking again. But you have like no room for it to deform. Necking. drop reduction in diameter with max load. This graph specifically, this is the real graph. It'll just break here. But because the calculation only is original area, this drops off. Because the original area stays the same, but it gets a lot smaller. So it's weird, I think. Right? Because this... It's kind of... It's rise of on 4 E equals... Yeah, this is strain. We have 60. So it, in reality, it like shoots up. What did they... I'm gonna say it later. Yeah, engineering strain. Like in true strain, it's something weird like this. But engineering strain, we go with initial. Like initial area, and we don't include deformed area. Because going by initial gives us a wider area, even though it takes less force to break the material because the area's gotten smaller. So like, if you calculate the area as it like normally is, right? Like let's say it's a like 2x2 square, area of 4, and that's stretched a ton. It'll get down where it has it becomes like a 1.5 by 1.5, let's say. We still calculate it as a 2. And it's still like holding more more stress per area. But it's kind of like less overall stress because the area is smaller. And then this, open to node, force. This is something I have to review because I get the idea behind it, but I do not fully understand it. Half a page of notes, halfway done. That ain't bad. I do want to say, last 3 lectures or so, I just don't understand the material at all. I know it's not that hard. I just... was horrifically sick with the flu. Bro. I didn't get my flu shot. Very stupid on me. 100% my fault. I hate shots. I should have gotten it. I should have gotten it. Hate shots though. And I was in the doctor's office for 4 hours. My appointment was like in 8:30 a.m. I was in there till like past noon. I was hungry. Like, hey, do you want to get your flu shot or no? And I'm like, nah, just not. Just it's fine, whatever. Just let me leave. Because they already like messed up something else. It was like a whole mess, and I was just tired. And I was like, no flu shot, and I get hit with the worst flu imaginable. Two weeks, horrendous sickness, constantly shivering, 5 layers of like bedding, comforter, blankets, 2 layers of clothing, still cold. Every so often, I take the hottest possible shower my dorm lets me. it still sucked. What does it consider A? A coefficient of thermal expansion. So what this formula does is basically the coefficient for how the heat affects expansion. Then the change in temperature, which makes sense. So that's if you go from A temperature to B temperature, that's how much that's the percentage that it should change. Times the overall length to give you the change. Makes sense. This may look scary, but it's low-key just... Well, total deformation is just one deformation plus the other. One type of deformation plus the, like, force deformation plus temperature deformation. Let's just say I go into the Arctic, I'm gonna a piece of metal, and it, like, goes, and then I whack it with a hammer. Well, that's not good out. Let's say I have, like, a compactor in the Arctic again. You're trying to compact metal. The cold would make the metal shrink, so it would have mad deformation. Oh, the formulas for are different for shin deformation because you take out the length. Because this is per unit. That's cool. That's cool to know. That's like cool to realize. Like to say, I conceptually get all this, but can I physically calculate it? Very past halfway point. And also getting to the stuff I understand less. This exam is only... I closed at the tab again. We're so happy here. This is so fun. You can see my mouse moving to, like, see the testing site. It's... Is that 240-minute? What? Okay, it's a 2-hour test normally. Oh, okay. No, I get it, I get it, I get it. Okay. I know this question's on the practice test, and I was glancing at it like, oh my god, I could not. If you ask me right now, before I reviewed any of this, what does the Poisson's ratio mean? This is just, it is just how the strain in one direction affects it. So like if I squish a marshmallow, it balloons out. Squish a plush, balloons out. Balloons. Squish a balloon, it balloons out. And then the z and x are equal because because it balloons out in both directions. That's cool. And then what is this saying? To kill myself. First. Oh, 1D and 3D. Strain x minus v times oy plus o. I'm not writing all of those because it's kind of understood that it's just 1 over e minus the strain in one direction minus v times the strain in the other two. Dependent. Homogeneous. I don't think it's gonna be that big a deal. And then worst case. And you can just kind of add them all together. That's kind of gross. Like, I get the meme of engineers generalizing, but saying the volume instead of 1 plus the change in x plus the change in times 1 times change in y plus 1 times change in z could roughly be equated to 1 plus each of them is kind of just crazy work. Then you kind of get crazy with it. What? What are we doing here? Shear strain. G. 7 more, by the way. This here is where I finally kind of lose it. I will not lie. We still have stress concentrations. Plastic. Plastic can be bad. Torsional. Yep. Nope. These 4, I was sick. Seek. I mean, that's fine. I got through like half them and filled up a page. Not well, but. And I do want to add. When I first reviewed this PowerPoint, I thought this was Poisson's ratio, which is the V. Uh, just now am I really realizing. It's not. I'm not sure what they mean by this, but I think it's like per 1 square inch, it's going to change that much. And you just factor out the directional. Cool. Hydrostatics when it's what, all around, I think? And then bulk modulus, related to the which is just this kind of flipped. Because this relates to how compressible a material is, because hydrostatic pressure basically just compresses it. Oh, okay. I think you remove the minus to ensure that. Then I don't like this one. You take P divided over. We just flip this. I get where it gets at. I don't like it though. Elastic modulus, Poisson's, and shear modulus. Which is just the change in shear. So it's the YZ shear equals the modulus of Y. Shear stress equal mod times strain. Okay. Makes sense. I'm leaving that one open now. Concentrations. Mode of force application is near the point of application. Now this makes sense. It spreads out. Complex structures like an onion spread. Would you plate versus point load? Oh yeah, if you just toss a plate on it, kind of spreads it equally. Roughly. I don't like that it's like bolded. That means it is definitely important. Saint Venant. Significant force up click node less import further. I read like a schizophrenic, but I'll be able to understand it. I mean, this makes sense though. Crushing, you would kind of balance out into like 0, and it would be closer to like kind of balancing out. Like if you karate chop thing, it's breaking where you karate chop because of this principle. That's a good way to put it. What is K? K values obtained from standard charts. So max stress over average stress. When you obtain them from charts. So if you know what the average should be, would just be the normal calculation. I can then use the K value. It kind of looks like I wrote chart, which is amazing. Oh, bars with fillets too. I did not like this. It did make sense though. It did make sense. It'd be a lot worse if it was just like a round full corner, which is why affiliates are implemented so often. You know, you kind of only see like harsh corners where it's basically unnecessary. Like think of all like the fully square things around you, like my PC, where the main square parts are things that just kind of exist. Like yeah, this like the far corner of my PC is not taking any stress. Like oh no, it barely has to hold the weight of a frog I put on top of it. Stuff like that. Like the fans, even they have like even the fan like housings have rounded corners. I think that's for aesthetics, but like the idea is still there. The idea is still there. Yeah, because the village just full radius. That makes sense. And this is just basic bearing stress, which is just thickness times diameter. Yeah, by little d specifically, because it's maximum stress, so it'll be in this area. Avoid sharp corners. Because you want it to equally push. Makes sense. Average normal stress. Oh, it does not explain this well. Okay. Uh, normal into chart. This really confused me when I had to do it. Into max. Making complete sense right now, though. 3:20 me, by the way. I have to wake up. I have to wake up in. I'm not gonna get 5 hours of sleep, man. I took like 3 naps today because I was so tired from working yesterday. So I could have the free time today to study. Example. Oh, that wasn't so bad. 5 more lessons. Because we already know. Less material. Move up here, goes back down. We should load until it is... Oh, they don't explain anything here. Ew. I don't like this at all. So we know you and you, so we can get you. Then we know what deforms 7. No, because deformation. Do we have the length? Yes. So this value from here to here is actually 7/500 minus from here to here, because it goes back down. We're just calculating this distance, honestly. Rounding it to the base. Which means you could just do, what, 7/500, maybe? I'll look into. Concentrations. Ooh, they put us in a lot. Just because these are not experience, heal all at once. I'd also like to add, we're at least 3 weeks beyond this in class material. This class isn't even that bad. I must add that. Generally making me consider material science. Well, material engineering, not material science. Those should be different. Man, I'm so tired of Arrow. That message my advisor. How change? Side face emoji. Okay. Plastic. Perfectly plastic tubes with stress countries will not yield all at once. Yeah, because if you pull something with like a ring around the ring, it stretches more. I was thinking about like plastic. Like we've all like tried to whip apart plastic, and we see how it like widens as it like stretches. I assume because the coloring is just a thin layer on the outside. So if the outside gets stretched or deforms in any way, or specifically stretched, and it kind of just puts a bunch of space in between them. I've been doing this for an hour. An hour, man. I want to point out this is my gaming channel, dog. Forcing myself to study through streaming because I know I can't focus otherwise. To be fair. To be fair. Studying with ADHD is like fighting for your life. So I don't feel all that bad. Like, really not all that bad at all. But what do you guys care? You don't have to watch. Anyway, back to topic. To topic. That's a lot of formulas. But I'm not sure what they all mean. Okay, let's equate materials. Just because we're gonna do that once. elastic. Okay, no, I'm writing this in the lines. I'm actually gonna give myself 30 more minutes before I go to bed. Which should be enough an hour for 10. Waking up in tomorrow is just like glance review and then practice exam review, practice exam, reviewing formulas, etc, etc, etc. Doing like the 10 important formulas. There's like one per thing that really matter. Not that bad. Half of what I say is actual nonsense, trying to convince myself. I'm not drawing a full line. I'm not entirely sure what I'm writing means. Max. It's kind of just nonsense and formula. Oh, PY is yield load. I love when Y represents something in shear. And also this. Okay. So you have to have each of these formulas. So when you're like, okay, the max is less than the yield. So it just won't yield. So it's just normal force equals stress times area. Which can be over K because K becomes 1 in this situation. Or no, because no. What? No. 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 That's max, not Av. God, I need to log in. Okay. Max less than Y, stress is below the yield stress. Remain the same. If you go max stress times area. Oh, okay, that's just the force. Why? Because of the other formula that is max equals K times force over area. So you could also just say force times area. Oh no, you could say max times area over K equals force. Yeah, okay, let's just rewrite the equation. Let's just rewrite the same equation. But then what it is the yielding, we'll just have the yielding force. You kind of cut out the middleman because it's yielding, which is separate from just normal force. So yeah, the force to yield is just the strain to yield times area over K. Maximum Y, it'll increase the maximum load. Yeah, the maximum load equals the yielding times area. And then you can kind of, yeah, okay, I think I get all that, mostly. Damage section comprised of last loaded if none of the members have yielded. Some means change from earlier, which yields the force. The unit is coming to the structure is capped at Py. After it starts yielding, it can't go past yield. Okay. We go alone. Here's when once enough members have yielded, which I'm assuming is like both of these. Okay, okay. This is quite new. 4 lectures of new. Can't be that bad. This is exam review with stuff I know, stuff I know, stuff I know and just reviewed, stuff I know and just reviewed, stuff we know and just reviewed. That, yeah. Makes sense, makes sense. Yeah. Yeah. The definition is the sum of definition in one plus definition in another. Okay, whatever. Material properties. It's just stuff I should write down. I should just understand this. I don't think it's gonna be like, oh, you forgot ln length over change length is actual. Yeah, I don't think it matters. Then demo, which I understand. And then V, which I mostly understand. A little off on that, but that's fine. I got this. Ooh, 7 pages. Which is roughly 4. Makes sense. Okay. Transmission shaft, axles, etc. Equilibrium. What is T equal? What is any of this equal? Oh, T is turning force. I don't know what I'm looking at. This is gonna be me watching a video later. Not on stream, because I am trying to do everything but watch other people's content on stream. I have before. I don't like it as much. I don't know if I can really I like to transform the content I watch, which is why I'm going through and kind of like explaining each thing. I'm someone who knows the rough idea of it. I don't know. I don't want my content to be like the people who just like in streamathons put on daily dose for their entire like sleeping or the how it's made. I don't know. That's why I haven't done like an overnight streamathon. That and setting up a camera to like watch me sleep is one a little weird. And two, I don't know. I don't know how to keep you guys entertained. Like an idle game might be cool. Like when you idle and it does stuff. I don't know how people no one would watch that though. Like literally no one. Plus I tune off the avatar. Because I'm tired. Anyway, back to it. DF is directional force, I think. Ah, what is DA? Y'all don't give me a bit area? Oh, is it a derivative of the force? Oh, it's derivative of the force. I'm actually stupid. I don't like this. Derivative of area for T. I don't. Like. Focus particular shafts and class. Torque will be inducing twist. Angular twist makes sense. When plain and undistorted. This is parallelograms. This shear strain. On each individual section, yep, because it changes. Cool. This is a lot of jargon. I'm trying my best, guys. I will go to bed in like 25 minutes because I need to get the least 4 hours of sleep, I hope. That's the goal. Watch me get like insane insomnia. What is A dash? Uh, it's just a change. What is outer radius specific though? Is that just into the edge? I'd like to say, oh, it's roughly. Oh, it's just YC. That's cool. Let's invalid at any radical position by replacing C with twist. I assume I'm gonna treat as a general formula. In terms of max, shear stresses using Hooke's law. Yeah. Man, this is a lot. So, but they had to say, yeah, just like these are what you really need, which is your strain, shear stress, and then solid and hollow. And what is J? J is polar moment of inertia. P angular twist over L. Y equals P over C Y max. Out impact, not import. Stress max equal T C over J equal P over C max equal TP over J. What is T? T's the, is T just torsion? Okay, so torsion times the outer radius over GA polar moment inertia. It's gonna be 2 pages. That's fine. Okay, and then equations. Solid equal J equal pi over 2 C to the 4 hollow equal J equal pi over 2 C2 to the 4 minus C1 to the 4, which makes complete sense. Cool. 12 angle of twist. It is very easy for me to say, like, oh, I completely understand that by just glancing at the lecture. We will see if I completely understand when I wake up tomorrow morning. And give myself 6 hours to completely understand material. I really can't even see the message. I'm moving my grades at a new window. For a few reasons. One, I don't want you to know my grades. But I'm not gonna lie, I have an 89 in this course. And 90 can't even bring it up to an A. I mean, I guess I need like a 91 here. Exams are 75% my grade, and there are 3 exams, so that is, what, 75 divided by 3? 12% my grade? No. 75 divided by 3? Each one's like 22%. No. 25. Oh, I'm stupid. Then still the fear of God in me. Holy. Waiting for my life is only 25% of my grade I just have tomorrow. My linear distribution. We determine the outer radius length and angular twist, which we already got that equation. I think. Alright, done again. Length. Shear strain from torque. Max over G. Big G coming back. Now I'm gonna need to understand all these relationships. Divided 4. Let's use some integral, which is a summation of the twist in one, twist another, twist another. So like if this is net 0, you have to get the twist here and twist here. Then negative for those. Q's. Connection, turn the torque and rotation between them. Turn the torque and rotation. Torque A, TA equals F R A. Force times radius here. G A over O A equals TB over OB. Cool. Rotating gears. Length that the gears rotate are equal. Specific gear turns, other gear turns in proportion. Action switches. Anyone who's done anything with gears ever or played any puzzle game knows that one. Rotation notion. B with respect to A. I don't know how that means anything, but 2 more. Huh. I think I might have skipped one. No. Nope. Chapter 14 was done a little early. That's cool. Oh, that makes me so hype. Indeterminate shafts. Indeterminate torque cannot be determined with statics alone. Seem familiar? Some of the statically determinate problems in Chapter 2. Statics, deformation, geometric compatibility. Design of transmission shaft. Example jam axles. To load and speed of rotation. Cool. Newton times meter second. T. Oh, T is torque. Wait a second. That's cool. Then you can do 1 equal 2 pi f equal frequency. Oops. I've got 2 other ones off this side, which is just other waves for power, which are more than likely not more important. if power, we literally just got this one. We already have that one. We already have that one. No, I'm not waiting on that. Squantation and circular shafts. Shaft release stress concentrations. Max is equal to K times torque times added radius over the inertia. Never use transition where fillet radius is near 0. Yep, because that's how you literally immediately get shear. That's so interesting. That's literally like textbook shear. Like anything you can get to spin on something else, that's what that is. Because it just makes the right angle. It's so easy to spin. Maybe you twist a knob. It like feel it's inside though. If I'm wording that correctly. Oh, I did that like 10 minutes early too. Well, we finished the general view. It just goes outside the shaft first. Shaft. Boost. Yield. Just one more torque. Move from outside inward. Unless it like snaps directly off, but eh. G1. Boost. Yield. Point. GP. Full. Yield. I'm sorry for that one, guys. I'm genuinely sorry. Radius of elastic core not yielded mat. No. Extra possible behavior shafts. In previous theory, seem slide no longer valid. For solid trigger shafts made of electroplastic. I'm not forgetting that equation. That equation is not getting recorded. That's a lie. Nope, I'm sticking to my word. Unless... Ooh, I gotta memorize that. Consumer problems, chapter 2. Don't fully understand that. To be indeterminate. Tensile, because you're testing the outward strength. Torsional loading. Pops out like clean if it's ductile. Brittle, it kind of just shatters in a way. Brittle is worse with normal. Ductile is best for shear. Shows concentrations. Remember, K is for if there's like a hole, so it's the force around the hole and concentrations. Understand that? Understand that. Nope. Nope. It's once excellent is insufficient. Does that calculate deformation angle twist in terms of that? Get most of it. Understand this part, understand this part, understand this mostly. Understand that, understand those mostly. Basically understand all that. Well, this has been an hour and a half streaming of my, not a first chunk, but a good chunk of my studying. I will not stream until tomorrow night, or I will pass away in my sleep. That's a joke. I will not actually pass away in my sleep. I intended it to come out more as like, unless I just pass out after my test. Because that's the end of my day tomorrow. To be fair, my test ends at like 9. I forgot to mention ADHD so bad I get double time. Which I did see some guy ranting about how like double time's not the true solution because you're giving someone who gets easily distracted more time to do a task that they're gonna get distracted from anyway. They find boring and it's an issue for them getting distracted. You're gonna put them in a room where they will find a way to get distracted anyway, because that's just how it is. Anyway, I'm done. It's 4. I'm tired. I gotta wake up early. 4 hours of sleep. 4 hours ain't bad for this. To be fair, I get the rough idea mostly. I don't know if I can do a practice exam. Whatever. Who cares? Indicate a failure surface by drawing a line or put angle on the specimen below. Brittle is diagonal, ductile is flat. By the definition of shearing strain. Strain caused by forces perpendicular to object. Basically, the force over area of the force is perpendicular to the object, and the effect on the force over area. Particular is loaded by torque T. The maximum shear stress occurs is loaded by torque. That's really an axis. Well, I think on the surface is the main one. The maximum shear. It breaks out in, so it should be on the surface. Yeah, just like stress. When an object, find what happens. Go the shape of the object changes. I mean, yeah. Yeah. Yes, yes. Absolutely not. Which means only normal stress. False. You can brute force and up-down stress with the condition. If the ultimate strength of material is 20, factor safety is 3, where's the allowable stress? You divide that by 3, because that's ultimate strength. Which would be what? 80? A given torque increasing the radius of a solid shaft will increase or decrease the maximum shear stress. Increase, I think. The central portion, ricocheting. It holds 3 plates together in double shear shown in the figure below. Yes, I know the blanks the case whether the quantities are 0 or non-zero, respectively if there's a temperature change. 0 and 0? No. A 0, non-zero, non-zero, 0. Person ratio is the V, and the V is the like ballooning and the squishing of an object and how it affects the other relations. Like let's say you pick a marshmallow and you squish it, how it goes in the like X and Y plane. Let's say you squish it along the Z axis, how it stretches out in the Y and X plane. For the stress state, determine the normal strain in the Y direction. So we have the ratio, and we have e equals 20. Okay, so I'm gonna get deformation by 20 times 70. This is what? 1 over e, 1 over 70 times... I'm not entirely sure. Oh, it never ends. It never ends. Stress strain diagram for ductile aluminum. Enable a yield strength on the strength of shear strength and modulus electricity on the diagram. That should be pretty easy. Similar torque overhead is applied to the shaft CD. The shaft AB is fixed. The diameter of the shaft is the radius the maximum shearing stress in shaft AB. Motion at D where the torque is applied. Okay, that's a struggle. Ooh, how many points is this total? 30, 30, 40. Ooh, that kind of hurts. Okay. Ooh, okay. Hey, it shouldn't be too bad. You know, think, yeah. So I know how to apply it, I can do it. I say when I look at this one and cry. This one shouldn't be too bad. We're going to plate H. Would just be like force, force. Here. So, you know, it's 40 in, and there's an out, out, and out. So there's 3 forces we don't entirely know. For electrostatic equations for this part is exactly indeterminate. Yes. Relates deformations in A, B, C, D, and E, F. Self forces A, B, C, D, and E, F. So the normal stress in E, F. Okay, I'll think about how to do that. This can be good night, everyone. Thanks for stopping by. Thanks for popping by, and goodbye.